I'll pass on to you, and I look forward to your great talk.
Okay, thank you, Ali. Good morning from California to everybody participating in the event. Glafki, I'm going to try to share screen. It looks like that works out fine. So this morning, I'm going to speak to you in this keynote about the general topic of why the moon, and speak a little bit about the activities of the Moon Village Association with regard to its architecture studies. So first, a little bit about the Moon Village Association. The association was created a number of years ago as a non-governmental organization based in Vienna, Austria. Its goal is the creation of a permanent global informal forum for stakeholders, including governments, industry, academia, and the public, who are all interested in the future extension of humanity to our moon. We foster cooperation for existing and planned global moon exploration programs, including both public and private. And we have a number of memoranda of understanding and are cooperating with various institutions, including colleges and universities around the world. We have some 600 individuals participating in our activities on an on and off basis, more than 25 institutional members and 40 countries around the world, with a wide variety of technical, cultural, scientific, technological fields. We have large-scale activities in several topics. One looking at the longer-term future of the moon, based largely in Japan. Another one looking at the key topics of cooperation and coordination, what might be called governance associated with the moon, through a group called GEXLA. And we have, of course, the architecture studies. I will just mention we also have a program for emerging space countries, which has been ongoing now for more than a year, bringing new participants into the global enterprise, which is the moon. So if you are interested, please do consider joining the Moon Village Association. You can see on our website a lot of relevant information about what we're doing and the opportunities that I just mentioned. So I mentioned the question of why land on the moon as sort of the organizing principle for this conversation. And I wanted to begin by sharing with you these images from a small pamphlet that was published in 1963 by NASA, when NASA was just getting started on the Apollo program and had to justify to the US Congress why billions and billions of dollars, 4% approximately, of the US gross domestic product were going to be spent on accomplishing a human landing on the moon by the end of the decade of the 60s. And the principal areas that were articulated in this small pamphlet, which is basically one long, very thoughtful essay by Robert Jastrow and Homer Newell, involved one, the science of the moon, i.e. the idea that the moon, which no one had visited yet, and very few, even very few spacecraft had been launched by 1963. One was the science of the moon, and this had to do with the idea that the moon represents an archaeological dig, one huge artifact, one huge record of the early impact history of our solar system, and that we could find out by going to the moon how the moon was formed, and whether or not it was formed by one of several means that were quite popular at the time among various scientists, or another. There was also the question in the time frame of the early 1960s of technological development, technological stimulation. If you have seen the video of President Kennedy giving the speech at Rice University, we do this and the other things not because they are easy, but because they are hard. And that by doing something like a landing on the moon, it would stimulate the best of American industry and innovation and academia. And of course, lastly, there was the ongoing Cold War. That there was a simple fact that the United States was in an ideological competition with the former Soviet Union, trying to determine which system of government would inspire the world to follow, a totalitarian state or a democratic state. And these are all the reasons that were articulated in this small pamphlet. That's all well and good, but we've been to the moon. That was back in the last human mission to the moon was back in the 1970s. Why should we be going now? Why should we be going again? And this is a central question, and it's remarkable how different the environment is for that discussion today, as opposed to where that discussion was almost 60 years ago. First and foremost, we are going to the moon in a very substantial way because there is a fundamentally new opportunity. One of the lessons from the Apollo program, from all of the lunar missions of the late 1960s and early 1970s, was a determination that the moon was dry and dead, that there was essentially no water on the moon, that there were no ice caves, vast ice caves like Robert A. Heinlein envisioned in his story, The Moon is a Harsh Mistress. There were no selenites a la H.G. Wells almost a century before Heinlein. It was dust, and it was rather obnoxious dust. However, all of that turned out to be both right and wrong, i.e., yes, most of the lunar regolith is dust and rather obnoxious dust, but as it turns out, at the polar regions in locations that are quite cold, there are permanent ice deposits that have accumulated in the regolith in the precise physical form we don't know, but these data from missions of the last 15 years or so indicate where the ice is located. This is a fundamentally new opportunity because water ice, potentially other volatiles, make it possible to produce fuel, to produce life support materials, water, and so on, far more readily than if everything had to be brought from the earth. And so the discovery of this resource represents a fundamentally new opportunity. As a result, in just the last few years, there has emerged an international consensus concerning a human return to the moon far broader than the competition between superpowers to determine the impact history of the inner solar system 60 years ago. There's a group which is called the International ISIG-G, International Cooperation. Sorry, I want to get this right. It's the International ISIG. Well, that's right. International Space Exploration Coordination Group. I got that. I missed the space. Sorry. The International Space Exploration Coordinating Group, which is chaired just now by a gentleman from the Canadian Space Agency, and was previously chaired by a gentleman in Japan, This group is responsible for putting together what is called a global exploration roadmap, largely focused on human spaceflight and other related missions over the coming decade or so. In the last year, in the last 8 months, the membership of this group has doubled, and it involves basically countries on both sides of the world, or all the sides of the world, and from both fully developed and active space programs to others that are just now emerging. So there is an international consensus. Moreover, there are fundamentally new capabilities and technologies emerging, and I'm going to highlight just this one because it's so striking, and that is the reality, which is only in the last 6 years. I think it's important to remember that the first flight of a Falcon 9 reusable took place in 2015. And so it's only been 6 years since the whole future of space was transformed by the reduction of launch costs from $20,000, $25,000 a kilogram to on order $2,500 a kilogram. So very, very roughly a 90% reduction in cost. There are more systems on the way. The Blue Origin is actively working on the New Glenn launcher, which is also a reusable first stage architecture. SpaceX, as I'm sure all of you know, is actively working on the Starship and will be along shortly, we believe. Later today, the very first commercial flight of the Spaceship One from Virgin Galactic is supposed to fly with Richard Branson, Sir Richard Branson on board. Very shortly, there will be a flight of the New Shepard from Blue Origin. And so an era of suborbital space tourism is getting started. China has recently mentioned that they are beginning to work aggressively on a reusable, low-cost, super low-cost heavy lift booster. Europe has mentioned that they are working on a reusable, super heavy lift booster. So the fact of the matter is that over the coming few years, unless there is a radical change, that there will be multiple very low-cost launch services available, and that these will be a mix of government and commercial launch service providers. This is a fundamental change from where everything has been before. Moreover, when you have low-cost launch, when you have low-cost access to LEO, you have the potential for much more affordable access to the moon. And so all of the details are yet to be worked out. I'm going to talk a little bit about some of those things in a few moments, but fundamentally, the ability to launch at a 90% cost reduction to space promises that we may be able to launch missions from low Earth orbit to the moon and to begin truly exploring and utilizing the moon, always with an eye towards respecting the lunar history and the environment and science of the moon. I recommend to you, if you're not already familiar with it, a wonderful organization which is a partner with the Moon Village Association for all moonkind, which is led by Michelle Hanlon. And in thinking about the moon and in looking at the moon, another aspect of low-cost access, new capabilities and technologies, is the potential that the moon could become a part of a larger economy of the Earth. And in prospect, as an example, the moon could become a crucial source of materials to build systems such as solar power satellites, which could deliver fully carbon zero energy globally within the next several decades. And of course, the moon is a proving ground for exploration beyond the moon. It's very, very hard to simulate space operations in low gravity on Earth. It just cannot. You can simulate higher gravity, But simulating low gravity is a matter of a few moments in the trajectory of a parabolic flight aircraft. But on the moon, you have the potential to develop and demonstrate technologies and systems that could be useful throughout the inner solar system and Mars and the main belt asteroids beyond that. And of course, the moon has long been viewed as a place from which science can be done, not just as a place to study. So the science from the moon, i.e. Both ultraviolet and infrared and radio astronomy, could provide whole new perspectives on the universe around us. And of course, going to the moon, living in the vicinity of the moon, on the moon for not just hours, but weeks, months, and years will be a driver for new human space capabilities. It's important to keep in mind also that we have an enormous wealth of information about 1G. We live in 1G after all. We have a little bit of information about humans in 0G, but only a little bit. No human has ever been born in 0G. And there is then we know practically nothing about what it's like for humans to live for an extended period in partial gravity, in 1/6 gravity, or much less 40% gravity. And so certainly our return to the moon will be a driver for human space flight capabilities. And of course, in the very long term, the moon could prove to be a place where humanity can settle. We've talked about space settlements and about the extension of human presence into the solar system for many decades. The moon could very well be the first place where we can go and stay. Within this context of all these reasons why humanity is going to the moon, the Moon Village Architecture Working Group is doing this year and last year and into next year a case study to define a reference architecture for the first permanent human settlement on the moon by 2045. Our goals include putting together the case study to better understand how the path forward might go following the current activities of various space agencies and corporate planners. We are looking at an integrated architecture, which I'll describe to you more in just a moment, and at the technologies and systems that would be needed. We're trying to define what are the missions and markets that could be served. The name of the architecture, which has been assigned, is Oasis 2045. It's an extension of the ISIC-G Global Exploration Roadmap and looks at this hypothetical settlement. These are the 6 zones. The principal area for focus in the case study is the lunar South Pole and the permanently shadowed regions where ice and other volatile deposits have been identified. Zone 3 is a Lunar Surface Science Observatory, a place to do those observatories I mentioned a few moments ago. Low lunar orbit, a place from which to travel from in the immediate vicinity of the moon. The cislunar space more generally, such as the libration points, and of course, Earth orbit. We started out the study with a set of high-level requirements. These have been refined rather substantially in the last few months. A lot of this material will be presented at the upcoming International Astronautical Congress in Dubai. The requirements include primary physical requirements, such as being able to come from and go back to Earth, being able to communicate with Earth, being able to conduct landing and ascent operations safely. Obviously, nothing can be done of any substance without energy, and so the availability of energy is crucial. There's a lot of ongoing discussion about how that might be provided. The case study that the Architecture Working Group is pursuing is focusing on solar. An interesting and somewhat detailed requirement is the need for surface smoothness. You're not going to be able to fly from point to point on the moon cost effectively if your purpose is to recover volatiles and use them to make fuel. So you use a hopper to gather fuel. You essentially burn the fuel that you've gathered in order to go back and forth from the location in the PSR. So local smoothness, being able to go from place to place on the surface, is a key requirement. And of course, anything on the moon in the way of a settlement has to be close enough to the permanently shadowed regions to make them accessible cost effectively. There are a bunch of secondary requirements, which are biological or human factors. These have to do with things that are obvious, such as air and water and food, also radiation protection. But in addition to those things, the questions associated with healthcare and the quality of life. And a key question is for a self-sufficient settlement is, how big does it need to be? 2 people or 1 person or 8 people living in a can buried under the lunar regolith is not really a settlement. So the question is, how big does it need to be in order to be a settlement? Operations type requirements included things like obvious things such as repair and maintenance, dust mitigation, as I mentioned before, surface mobility. There are also a whole range of requirements associated with self-sufficiency. Obviously, you cannot afford to throw things away on the moon for not just the obvious reason of the economics, but also because you cannot contaminate the moon by conducting operations and by living on the moon. And if you throw away critical elements such as carbon, then it's impossible to be cost effective. Then self-sufficiency has to include food production. Our focus is on conventional agricultural systems, not entirely conventional, obviously, but fundamentally agricultural systems, because those are ones that could be available within the next 10 or 15 years to support a settlement 25 years from now. And then, of course, there's a whole range of mission and market activities that have their own requirements, which, if the lunar settlement, Oasis 2045, is to be economically viable as well as technically possible, then it has to be able to have customers. So it has to be able to provide goods and services to a range of missions and markets. In terms of the self-sustaining population, our baseline, which is drawn from past studies of the level at which human populations can be genetically self-sustaining, is about 40 individuals as a baseline. We do anticipate that the definition of a settlement has to include children. And so there's a plan that the people living on the moon will have children. Other people will leave the settlement, others will come, but that over time, by the end of the century, there will be on the order of 120 individuals living and working and raising their families more or less permanently on the lunar South Pole. In addition to the human population, there's a requirement for self-sustaining populations of a wide variety of other species, plants, fungi, animals, insects, and so on. The sort of fundamental sine qua non is that such populations have to be sufficient to produce 2,500, 2,700 calories per day. That, by the way, leads us to an implied but very firm requirement, which is how much agricultural land is actually required. On Earth, sort of the on average value, taking into account summer and winter, availability of water, rainfall, and so on, is about 1 acre or 4,000 square meters per person on average. It can be more if the soil is poor. It's very seldom very much less. This translates in the case study to about 1,000 or 1,500 square meters per person because of the ability to manipulate the environment. You don't have to have months of dry or months of cold, or you have no winter on the moon. You don't have to have a winter on the moon unless you choose to. And so we've taken this down to this level, and this is the basis for the requirement for agricultural area for the lunar oasis. The first thing we did with these requirements was to think about where at the South Pole. Key drivers for location included the energy, thermal management, getting rid of waste heat, not being too cold, access to resources, the local smoothness of the terrain, as I mentioned, having a view of the Earth. We think it's very good or very important psychologically that the both settlers and visitors be able to see the Earth in the sky. And this is the location. So this is the vicinity of the South Pole of the moon. The South Pole of the moon is essentially at the triangle, a little bit higher up and to the right, but the triangle on the rim of Shackleton crater over to the right of this image. These, by the way, are just enormously valuable data sets from the Lunar Orbiter Laser Altimeter, LOLA, instrument from the Lunar Reconnaissance Orbiter. These data and others from fabulous missions from Japan and from India and China are all accessible online if you want to study them. I like this particular image very much because this area, as you can see the legend in the lower left-hand corner of 20 kilometers. So this is approximately 60 kilometers by 40 kilometers in area. This is just about exactly the area of the Grand Canyon on the Earth in the United States Southwest. Key difference between this area, which is about the same as the Grand Canyon system, so the maximum difference in elevation from the rim of the Grand Canyon to the I have a question, but I'm going to come back to it later because it relates to human health. But thank you. I'll come back to that in a few minutes. The maximum difference in elevation from the highest point in the Grand Canyon system to the floor of the canyon is about 2,500 meters. The maximum difference in elevation in this region of the moon is about 5,000 meters. And so it's about the same area, but the difference from the highest peaks to the lowest crater and canyon floors is twice the difference in elevation of the Grand Canyon system. So it's truly if you were somehow able to stand on the rim of Shackleton and see the floor, it would be a fabulous view. Unfortunately, that will be essentially impossible with human eyes because the floor of Shackleton is permanently shadowed. But nevertheless, there is on some of the edges of Shackleton, some of the ridge lines of these enormous mountain features, there's a periodic sunlight, and the sun rising from the side opposite the Earth on the ridge line to near De Gerlach crater, I think will be an incredible view with essentially a mountain range rising 2 or 3 kilometers from the darkness into the sunlight in a matter of a few hours. So I think that the location is really a spectacular one, and it happens to be where the ice is, and therefore it's driven by the requirements of the water ice. The habitation system of Oasis is called out there in the lower center. Some of the other features are identified, but I'm going to come back to those in a moment. I wanted to highlight that collection of energy is going to be a real challenge at the lunar South Pole, because just like the polar regions of Earth, there are periods of light and darkness. times when sunlight is or is not available. And so collecting, harvesting sunlight and delivering it to a substantial operation, to a settlement and so on, is going to be extremely challenging. Just for to speak a little more to the terrain, we've done a series of terrain maps. These are basically the topological maps of these locations. You can see highlighted the lunar south polar ridge line going from Shackleton crater in the general direction of Sverdrup crater, just to the north of that, to the earthward side of that, not north, but to the east. Actually to the north. Well, I guess from the lunar south pole, just like on Earth, from the lunar south pole, all directions are north. But the is our initial target with regard to ice mining. It's a diamond-shaped area, sort of in between Shackleton and the Gerlach, and up a little bit on that line. This is a close-up of the location, which I highlighted a moment ago. Namely the far edge of the lunar south polar ridge line. In the upper right-hand corner, you can see the just the beginnings of the rim of Shackleton crater. And now zooming into the area in the box, this is the particular location of interest for the case study for the Oasis 2045. There are a number of very interesting features. In particular, in the upper left is the actual site that's been chosen for the Oasis 2045 habitation. It is a crater feature, an impact feature on the earthward side of the South Polar Ridge, just as it starts to drop off. On the lower right-hand side is a site that's been selected for the spaceport. This is at a distance from the Oasis in order to assure that any launch or landing mishap cannot cause damage. And then in between these two is this very interesting impact feature, which is almost shadowed from the sun. It's not quite a permanently shadowed region, but the temperatures in this, basically a hole, a pit, in between the arms of the ridge line, are on the order of 100 degrees Kelvin, and so it's a very convenient location to place a cryogenic propellant depot where it's naturally cold. And this then substitutes for the topographical map, a false photograph rendering of the LOLA and the LRO and other data, which has been synthesized, is available from a website at JPL, indicating what the actual locations look like, the spaceport, the hole where the cryogenic propellant depot is planned to be, and the habitation site itself. And you can see in the lower left the distances between the habitation site and the spaceport. It's about 4 kilometers from the habitation site to the propellant depot. It's about 1 1/3 kilometers, and then between the latter two. So the concept in this location is that there would be multiple habitations in close proximity, that there would be the maximum use of local materials for habitable volume, that they would not be imported, but rather that the pressure vessels would be fabricated in situ, that there would be separate habitation and separate volumes for habitation, for agriculture, for visitors in the system. And I'll show you an image in a moment of what it kind of sort of might look like, and an artist's conception. Operations would include resource extraction. A key question is, how do you keep the volatile region? How do you keep the volatiles in the ground if you're operating near and you're warming up what is otherwise a 40 or 50 degree Kelvin permanently shadowed region? Well, in the case of this concept of operations, the ice-bearing regolith is planned to be returned to the main complex of Oasis 25 for processing. So the most energetic operations would not take place at the permanently shadowed region, but rather that the ice-bearing regolith, and we don't know the exact structure of any of that as yet, so there's a real set of questions still to be answered by the upcoming robotic missions to the South Pole, but that those things would be returned to the outpost rather than being processed in situ. And then a range of other facilities that would be associated with operations. As I mentioned, solar energy. We're anticipating, and I'll just go back here for a moment, when you look at the differences in elevation between these locations, and in particular between the power stations and the location for the ice mining, we anticipate that running power cables, and especially given the changes that are expected over time, would be highly problematic. And so we're currently looking at using wireless power transmission for making a local wireless lunar power grid. And I'm going to wrap up here just in a few moments. This then is zooming in on that upper left site, the Oasis 2045 habitation site. These are, again, LOLA data, but extracted to get the topographical map of what that impact feature looks like. As you can see from the upper cross section, and the one on the left, it's very much on the edge of the ridge line, and so the upper edge of the crater is significantly higher than the lower edge. And the plan for the Lunar Oasis 2045 is to have the basically the people, the habitation systems embedded and built on the upper rim of the crater, and that in the bowl of the crater would be the agricultural habitation or agricultural biosphere. The concept that we're looking at the moment is rather novel in the space community, but is well known to students of geometry as a spiral of Archimedes, so named because Archimedes was the mathematician who came up with it. The idea is to basically have a pressure vessel like the pressure vessel that has worked for hundreds of millions of years for nautiluses back in ancient the time of the dinosaurs and before, ammonites, and more currently in gardens all over Europe and the world, snails, where you have a series of chambers. Each one is sealed. Each one builds on the ones before it. And so this spiral would be where the agricultural systems would be. This is what that would look like in situ, and the concept still being developed is to essentially build into the sidewall of the crater, and this area for habitation systems would be looking earthward, and individuals near the habitation systems would, on a good day, be able to look into the earthward sky and see Earth low in the horizon. This is an artist concept, which has been done for the Moon Village Association, showing what that kind of sort of might look like. It's got some good features, and it's got as an initial concept, and some that are not quite so perfect, but nevertheless, it gives you kind of a feeling for what the Oasis 2045 concept is at the moment. We've identified a whole range of building blocks, the systems that I mentioned a few moments ago, in terms of human systems and transportation and utilities and so on. I just wanted to highlight that we are looking at the economic viability of such a settlement, recognizing that there are many unknown unknowns, but nevertheless wanting to go through and think about this. One of the most striking consequences of the low cost access, which is now emerged just in the last 6 years, is space tourism. And of course, I spoke a few moments ago about the knock on wood, upcoming and successful flight of Sir Richard Branson for suborbital space tourism, one of the earliest mission markets for the Starship when it's completed is a fly around the moon, so lunar tourism. And we're doing an end-to-end lunar travel and tourism use case, beginning with Earth departure, going through a visit to the Oasis, and finishing with Earth return to try to get a better handle on what the economics and the technical requirements for people visiting the moon would be. It's a huge change from where things were, for example, in the 1980s, when it was envisioned that only US and similar sponsored astronauts could go to the moon, and the cost would be I don't know, hundreds and hundreds of millions of dollars per person. But we don't yet know what the cost will be to go to and from the moon in the current situation. But we do know that there is a market, and there is a market. We know there is a market because there is already somebody, a billionaire in Japan, who is contributing hundreds of millions of dollars to the development of the Starship in order to go to the moon. So the existence of the market has been proven. The question is, what would be the price, and what are the costs, and is there a business model there? And we're going to be exploring that, working with the recently formed economics working group, which is being led by Derek Weber for the Moon Village Association. We've got a concept of operations. Because of the shortness of time, I won't go through all of this. It basically is just a way of thinking about how do all of these pieces interact, and how do they relate to one another in a physical sense. But there's also the functional sense. We've constructed a functional modeling framework to allow us to connect, for example, how many visitors to the moon per month. What does that mean in terms of transport and requirements for propellant? And then how do the requirements for transport and propellant impact or inform decisions about the production of propellants from the water ice, and therefore the mining of the ice-bearing regolith? And so we see this as sort of of course, as an integrated ecology and market on the moon. And so all of these different aspects impact others, and what we're beginning to look at is how does A impact B and lead to C in the 2045 timeframe. Just as an example, at a workshop we held last December, Yushnoi State Design Bureau presented this very nice concept for a fully reusable in-space transportation infrastructure. I'll just mention that the detailed results of that workshop, 3 days, about 16 hours, participants from around the world, are all available on the MVA website. As I said, we're looking at the relationship among the different systems and how A leads to B and so on. And it's sort of the key background on all of this is power. Nothing happens without energy. Plan forward during the coming months. We are finishing up the current sets of studies. There'll be a series of presentations in the fall, including and beginning with the International Astronautical Congress and additional meetings and workshops. We're hoping to hold a workshop later this summer, and a follow-on workshop to the one that was held last December. And then working results will be presented at the upcoming Moon Village Association virtual workshop and symposium in early December. And that's it for the presentation.
Thank you, John. I think we have a couple of questions here, and I've also noticed a couple of few questions on YouTube, so we can start with the ones here.
Please.
So the first question is, what will happen with the health of children and child development on the moon?
So the simple fact is no one knows anything or almost nothing, only very, very tiny amounts about partial gravity, generational genomics or developmental evolution. So nobody knows anything about that yet. So we're making some high level assumptions, and then we're exploring through this case study what are the consequences of those assumptions. We will be providing within the context of the Oasis 2045 system architecture some specific ideas for providing, I'll say, Earth gravity on an interim or occasional basis, but not on a permanent basis. And then we're just going to have to wait and see, and in order to resolve whether or not this is really close to what a settlement on the moon might be like, or whether or not there are going to be more aggressive measures required. But at the moment, no one knows. We're going to provide for artificial gravity as an acute treatment, as well as, of course, for exercise, the same way that the astronauts and people living on the International Space Station exercise often and daily, frequently and daily, and we'll see how it works out.
Thank you. The second question is, why have we chosen the South Polar region to settle?
Yeah, so there's a strategic reason and there's a simple reason. The strategic reason is that the identified permanently shadowed regions, and therefore the deposits of volatiles at the South Polar region, are more plentiful and more readily accessible than at the North Polar region. Just true. Either one could have been chosen, but on the practical side, the fact of the matter is that almost all of the space agencies of the world are going to the South Polar region, and so if we wanted to take as our starting point the global exploration roadmap, which all of the space agencies are sort of collaborating on building on an ongoing and live basis, then we had to start where everybody is going. We want to build a restaurant. We're not going to build it out in the middle of nowhere. We're gonna go someplace where the customers are.
Great. So how do you envision the balance of incentives like mining versus contamination of the moon, and where does the line between, I guess, profit and scientific study land?
Yeah, so this is another reason why we're not anticipating, at least at the moment, the concept of operation for lunar ice mining and resource utilization involves going out and collecting the material, but then preserving it and bringing it back and processing it inside a sealed bubble. So none of the processing. There may be vehicles going back and forth from the Oasis to the ice mining site repeatedly, but there's not going to be. The plan is that there would not be anything resembling a big open pit mine or any of those images that one has from the mistakes in terrestrial mining driven by economics. And we think that having things closed up, having a concept of operations where you don't do a lot of the processing out in the open, but you do it all within a bubble, actually facilitates good economics. You don't want to lose any of the water. You don't want to lose any other volatiles. And frankly, once you've collected regolith, then you've processed it, you've raised its temperature from 40 degrees Kelvin to 260 degrees Kelvin, you're halfway to turning it into walls and roads and other systems. So energy is money and time. And so once you begin processing a cubic meter of regolith, they're all relatively similar as far as we know at this time in a given region. So we're just going to hold on to it until we're done with it. And so our hope is to minimize, for good economic reasons, the degree to which there is any kind of contamination, with an eye specifically towards a sustainable moon.
I guess shifting away from mining, but something that is rather relevant today with the Virgin Galactic launch. One of our participants is asking, do you foresee there being regulations for space or lunar tourism, be it similar to immigration laws or other type of regulations that would be formed around this area of activity?
I think there has to be. There are absolute. I don't know what will be the governing body for such regulations. It might be very well be the service providers. Nobody's going to the moon without first getting off the Earth. Nobody goes to a geo and operates a communication satellite without first getting an orbital slot and a spectrum. So the International Telecommunications Union, which was managing spectrum terrestrially, and before spectrum and radio was managing telegraphy, sort of grew into becoming the body that manages orbital slot assignments. So it may very well prove that a coalition of the launch service providers sets the rules of the road with regard to people traveling throughout the cislunar space. But to be determined. I think there absolutely must be regulations.
Another one of our participants is asking an interesting question about the structures you showed. So the images that you showed, a lot of the habitats are on the surface, and we know that the radiation environment and the temperature environment on the moon is very harsh. So a lot of other concepts focus on underground facilities. So do you think that these facilities in the future would be on the surface or underground?
Yeah, so the artist conception that I showed and a number of the early artist conceptions are all on the surface, but the better reflection of what the case study is actually looking at are these pueblos, these dwellings of indigenous peoples before the modern era, where they dug into the sides of cliffs, they dug in under the ground to avoid the heat of for example, the heat of the day in the Middle East. These things are really good examples. And although we're trying to avoid radiation, we're trying to avoid the thermal extremes, nevertheless, I really believe that those are the right models. But on the other hand, you want to provide a view. Again, you don't want to go to the moon and live in a hole in the ground. And so by thinking about putting these kinds of habitations on the side of a crater rim, where the upper rim of the crater is significantly higher than the lower rim, and it faces towards the Earth. So we're trying to have our cake and eat it too, have a very significant degree of sort of digging in, but then just like the indigenous peoples, I showed a picture in my presentation of cliff dwellings of the Anasazi people of the American Southwest from 1,000 years ago. That, by the way, was a little village of about 150 people. So it's about the right size in terms of the number of rooms and the amount of space, that it will be able to look out and towards the Earth. And so you'll have your protection, you'll have your thermal stability, but you'll be able to look out of a window and see the Earth in the sky. That's the concept.
So these will be our last two questions. The first one is about manufacturing on the moon. So what are the technologies that are needed to manufacture on the moon, and what are the major environmental challenges associated with lunar resource utilization?
So certainly at the root of everything is handling and working with regolith, turning it into the basic structural systems, roads, landing and launch pads. But then at the next tier, there's the more sophisticated level of processing regolith, turning it into pressure vessels that can be used either for habitation or for chemical processing or for tanks to handle and manage fluids up to and including cryogenics. There's a whole wide range of individual systems and technologies, such as manufacturing solar arrays out of lunar silicon, structural systems out of lunar iron, and so on. There are actually groups now studying these, and there were some wonderful presentations at our workshop last December. And so for more details on these different areas of lunar resource use, please look at those. But from our perspective, in terms of the concept of operations, as I said, it's our plan that almost all of these activities will not happen just out on the lunar surface in an uncontrolled fashion, and that rather that we'll bring these the resources in and we'll process them in a bubble, and basically a lunar manufactory. And the reason to do that is not to lose the volatiles, not to lose carbon or lose sulfur, lose phosphorus, lose water, which otherwise you could use many, many times. So all of this, those things are all precious on the moon. So we think that good sustainability will actually correlate with good economics.
And to kind of close the question and answer session, I think this is a very broad question, but it's interesting to end on that. What, in your view, are currently the biggest challenges for lunar exploration to solve in the short term?
In the very short term, I think it's going to be just kind of like a hyperactive extension of the 60s and the 70s. So there'll be lots of individual missions. There'll be lots of activities ongoing, a rover here, a lander there, an orbiter here. I think very soon we're going to, in the almost immediate future, we're going to need to sort out the data and information architecture for the moon, basically the lunar Wi-Fi, and there are already good efforts to begin doing that. Secondly, I think almost immediately, certainly within the next 5 or 6 years, there will be regular missions to the moon with people. And so we'll need to start sorting out who goes where and how do we, on the one hand, assure that we don't interfere with one another, but on the other hand, assure that we can help one another, that in the event of an emergency or a problem, we have standards for atmospheres, for airlocks, for power that will allow us to cooperate where we need to. And I think these things are going to be crucial in just a little while, so that they can inform design and development of systems that will be operating 5, 6, 8 years from now.
Thank you, John, for the presentation. It was a great overview to really start the workshop, and we touched on a lot of the topics that we will be focusing on during the week. So I hope all the participants, I think they all enjoyed and they're all thanking you on the chat as well. With this, we will close the public part of the session today. Participants that are on Zoom should stay here for 5 more minutes. We want to tell you what happens next. But thanks again for everyone that was watching on YouTube, and thank you, John, for the presentation again.